Good morning, sir.
Hi, good morning. Tarun, huh? Okay. Tarun, how are you?
Fine, fine, sir. How are you, sir?
I'm good, sir. Tarun. Okay, I'm just adding you as a presentee. Please add
Okay,
other.
sir. Okay, sir.
Don't give this access to anybody else. Okay?
Okay,
You.
okay, sir.
I think you are already present here. No.
Ma'am, done that, sir.
No, you are in the attendee list only. I'm just adding you as a
Oh,
presentee.
okay, sir.
Okay, done. Okay, good morning everybody. I think everybody is inside. So we'll just start class. Okay, shall I start?
Yes, sir.
Yeah. Okay. Today, in the last class, we have already seen the continuity equation derivation and to some extent the fixed law of diffusion. So I will now try to derive this on a live board. So confirm me whether my live board is visible to you or not. Okay, my live board is visible now.
Yes,
Yes,
sir.
sir.
Yeah. Okay. Yeah, we'll continue now. Okay, first continuity equation. Why we have to derive this equation? In order to see the flux, how the flux is changing with respect to spatial coordinates. We already know there are three-dimensional spatial coordinates, x, y, and z direction. You may have noticed this in your notes already. So I'm just drawing here. Consider the graph. Let's see. This is x direction. Maybe this may be a y or z direction we can consider. Otherwise, we can consider this as a y direction. Okay, three-dimensional spatial coordinates. Consider in this a cuboid is there. Okay, cuboid is there. So how the flux is changing with in this cuboid, we have to study this one. For example, this is the x direction. Okay, this is the x direction and this is z direction and this is y direction. So we can say where is the origin of x direction? Origin of x direction is here. Okay, origin of x direction is here. Then we can consider this entire region, x region, as delta x. Okay, when x is 0, delta x is nothing but the maximum value minus minimum value. Minimum value will be obviously 0. So the what is the value of here, x minus this value here. So origin here is x. Okay, so this is delta x, and with respect to, as you can see, this is the y direction. uh, y direction, so delta y will be this region. This will be delta y, and same the vertical region is the z direction, so we can say this is the delta z region. Okay, change in the particular z direction. Then usually in the mass transfer we have to measure the mass transfer operation in terms of fluxes. Okay, here we need to concentrate more on the fluxes. So first we will just define where the flux are changing. Initially in all the modeling or simulation, otherwise in any process, all the inputs are known, whereas outputs we can't predict. It depends completely on the inputs we have given. It depends on the system. It depends on the surrounding environmental conditions. So now we have to define the inputs in the x direction. For example, this is entirely the x direction, we already shown in the three spatial coordinate system. So when the flux enters in this direction, okay, this is the origin. Since this is origin, we will denote this as flux of x component of flux at x. Okay, this is the meaning of this nax at x. Since origin is we are indicating as x, so we are taking na of x component of flux in the direction of x. This is the meaning of nax at x. Sorry. So output will be this one. So output, it will come like this. So flux, whatever the transformation already happened inside will happen, and the output will give outside. So here this is flux, the same component. Since this is going in the x direction, we will consider nax. But the output will change. How it will change? So nax is entering at x, and the change is already happening inside. So this change we need to incorporate. What is this change? This one, delta x. So we will indicate this as x plus delta x. So similarly in the y direction, in the z direction, which is vertical direction, the origin will be here. The origin is here for this cuboid with respect to z spatial coordinate or z direction. So we will The input will be NA of a Z component. Since this is in a Z direction, we will indicate it as a Z. So NA at Z, NAZ at Z, since this is the origin. So output for the spatial coordinate is here, NA of Z component at Z plus delta Z. Okay, similarly for the Y direction, see here Y direction is this cross section. Okay, the diagonally it is showing towards for the X and Z it is in a diagonal direction. So diagonal direction delta Y is this one. So it will move like this. NA flux will move in this direction. So here the origin of Y. So NA of Y component, flux of Y component at origin, which is Y. Okay, whereas the output for this direction will be this one. So output is NA of Y component at Y plus delta Y. Okay, these are the notation schemes which we will adopt in derivation of continuity equation. Hope this notation scheme already you understood this one. So I am just quickly going to the next slide. Here the first step in defining so is mass balance equation. We need to conduct the mass balance around this cuboid. So what is the mass balance? We already have seen this mass balance in IPC, instrumentation and process control. So mass balance will be the mass balance equation. So mass balance, what is it stating? Rate of mass output or input we can write in other case, but symbols will be signs will be different. So rate of mass output minus rate of mass input plus rate of mass accumulation. Rate of mass output minus rate of mass input plus rate of mass accumulation is equal to rate of mass generation. Mass generation. Okay, this is the overall material balance equation. Okay, in a simplified terms, then this equation in a symbolic manner we can write that rate of mass, m is denoted for the mass, but when rate is coming we will denote m dot. Similarly in the heat transfer, q, capital Q is denoted for heat flux. Okay, rate of heat transfer, whereas small q or a capital Q dot is indicated for rate of heat. So similarly here for the mass we will indicate small m, and for the rate of mass we will indicate m dot. So m dot out, mass output according to our previous equation, minus mass rate of mass input m dot in plus rate of mass accumulation m dot accumulation is equal to rate of mass generation. Okay, we will give equation numbers from the initial numbers. So this will be the first equation which is defining the mass balance equation, and symbolically when we express this equation we will get a equation 2. Okay, then we need to just I'm showing in a different color. We need to expand this. What is this m dot? What is this m dot in, m dot out, and m dot accumulation and m dot generation in terms of our these symbols NAZ, NAX, NAY. In these terms we have to evaluate, we have to substitute those terms in this equation. So from this equation 2, so first component here will be NA output, m dot output. So we need to expand this one. What is m dot output? So m dot output is nothing but output is equal to here, sorry, we will define input first so that you can clearly know what are the inputs first. So we will consider m dot input first. M dot in, since it is starting from origin, defining inputs are very easy, and after defining these inputs it is very easy to define the output. Simply we have to replace wherever x is there, we have to replace it with x plus delta x. So here we can see what is m dot input. M dot input is equal to, so in general speaking, we have to express every flux in mass transfer as molar flux. Since in all problems we will be given the units of flux in terms of molar fluxes only. So units are mole per meter square second. So first we have to define what is m dot. See, m dot is equal to, we have to express our mass flux, molar flux. N is denotation for molar flux. So whose units are mole per meter square second. So according to m dot, what is the units of m dot? M dot units are nothing but kg per second. Okay, any term, any variable which is called as rate means divided by second. You need to remember this, divided by second, which indicates rate means divided by second. Whether it may be heat quantity, when we are saying heat rate, it is joule per second, which is nothing but what? When we are saying a mass component or a molar flux, when you are saying molar rate, which is mole per second. When we are saying mass rate, it is kg per second. So units for m dot will be kg per second. So m dot we need to express in kg per second, but we have a quantities in terms of fluxes, molar fluxes, whose units are mole per meter square second. But what we have to do, we have to replace this mole at the same time this meter square. Meter square can be easily replaced. How we can replace easily meter square? We have to multiply with area of the cuboid, so whose units are meter square. We can just cancel out this meter square. The left out term will be mole per second. So we have to replace this mole with kg. Now how can we replace that one? So we have to replace this using molecular weights, whether it may be MA or MB or MC, depends on the particular species. The molecular weight will have a units of, I'm just writing due to lack of space here. So units of kg per kilomole or mole per gram per mole. In the either way we can write, or gram per mole simply. So now what are the units for this equation? So we can just cancel out this mole and this mole. The left out term will be gram per second. Okay, mass rate can have a units of kg per second or gram per second. In either way it is possible, because mass can be measured in kg and as well as grams. So this is the overall unit scheme. I hope this you understood. So we can write m dot in a general term. M dot is equal to, we have to multiply with molecular weight. Capital M means molecular weight multiplied by the flux of any component into area. So this is the basis for expanding those m dot in, m dot out, and m dot accumulation, m dot generation. So our first term in this equation, you can see in this equation our first term is this one, m dot out, and m dot in we have to write first. So how we can write that m dot in our present cuboid terminology? M dot inside, which is going inside, we already stating here, we have to multiply the term with MA. Since for your mass transfer operation only two components are there, first we will write for A component A. So this is a molecular weight of component A multiplied by, so molecular weight is not at all a variable, it is constant. When we are saying the molecular weight of A means it will remain in any system, whether independent of any process, the molecular weight will remain constant. So every time we don't have to multiply with molecular weight, just we will take common outside. So in initial in the input, what are the terms entering? It is flux component X, which is entering a X direction. Okay, so we have to multiply with area here. So the units are meeting here according to units. See, according to units we already multiplying with m. Okay, this m is belongs to this m, and nax we are writing, this n is belongs to this one. So we have to write area is in x direction. So what is the area in x direction? We can see this is the x direction, it is moving here in the x direction. Therefore the area for this cuboid will be delta z into delta y. So we need to take the cross sectional area. So cross sectional area for this region is this one. So delta y delta z. So for one direction we already written the equation. So for the next direction, that is y direction, we have to write. So sum of the three dimensions, three directions, okay, we have to write. So NA of now for the y component, which is entering in the y direction. Since it is input, only we have to write y. So area in the y direction will be delta x, cross sectional area is delta x and delta z. Then for the similarly for the next component, which is z component, z component of flux NAZ in the z direction multiplied by the area, cross sectional area in the z direction is delta x and delta y. This is the overall input equation. These many inputs are entering inside the that cuboid, particular cuboid. So these three quantities we have to see. So I think this is equation, yeah, equation 3 this is. Okay, we can give this as a equation 3 number. Okay, I'm going to the next slide. So we have to write now for the output m dot output. Okay, m dot output. Okay, m dot is according to our previous equation, which is m into n into a. In this form only we have to write this equation also, m dot output. So here also same, molecular weight of a is constant, we have to take common. Then flux which is entering outside, we can see from the cuboid the outputs are nothing but this Na is origin, Na which is entering at origin. I will show in different color. So this is Na which is entering at origin is x, whereas output is Na x at x plus delta x. Since it is crossing this value, this delta x region it is crossing, so we have to add the delta x value. So all the outputs will be at x plus delta x, y plus delta y and z plus delta z. So now we have to express our quantities in output region. So this is Na x at x plus delta x, so which is multiplied, which needs to be multiplied with area. So since this is x direction, so we can write cross sectional area as delta y and delta z plus summation of this with the next component of flux, which is NaY at y plus delta y into multiplied by a cross sectional area in the y direction, which is delta x and delta z plus, I am writing the down. So y z component of the flux NaZ entering our output from the z plus delta z direction, which is multiplied by a cross sectional area in the z direction is delta x delta y. So simply if you can see the difference between equation, this is equation 4, yeah, this is equation 4. If you notice the difference between equation 3 and equation 4, only the difference is I will show in different color. Only the difference is every term are same. Only here x is changing. Here x is there. Here y is there. Here z is there. Whereas in equation 4, you can see that only these terms are changing. X plus delta x. Here we are adding y plus delta y, and at the same time z plus delta z we are adding in this equation. Only a slight difference is there between input and output. You just have to notice this one, and when you just able to write this equation 3, you can simply write equation 4. So this is simply, you need to remember that we have to change the variables x to the x plus delta x, y to the y plus delta y, and z to the z plus delta z. Okay, simply we have to change. We have to write the equation 4. And the next term in our mass balance equation is rate of accumulation, which is denoted as, okay, m dot accumulation, which we are denoting with m dot acc. So accumulation term, how the accumulation will happen? Accumulation will happen only in the x region or y region or z region. We can't say it can happen in the whole total cuboid. Total cuboid, when you consider this as a reactor, simply as a reactor, this whole cuboid, when you consider this as a reactor or simply a bowl which is just mixing a wheat flour, okay, wheat flour, then accumulation means it can accumulate, that particular atta or the wheat can accumulate in any direction. Okay, we need to calculate that accumulation. What is that accumulation? You can just treat this cuboid as a bowl, simply bowl or a reactor. Someone is mixing wheat flour inside. So when we are mixing it, some of the wheat flour will just attach on the surface of that particular bowl. So we can treat that as a accumulation. That's a simple example for the accumulation. So next, now accumulation can only be possible inside the total volume of the cuboid or a simple bowl or a reactor we can consider. So change in mass, okay, with respect to time. So accumulation term is dependent on time. So change in mass with respect to time. So what is the definition of density? Density is equal to mass by volume. Since we are writing for component A, we are writing rho A is equal to ma by v. So simply from this equation we can write what is mass. Mass is equal to density multiplied by volume of the particular solution. So we need to substitute this here. So this equation, accumulation term, is equal to mass, we can replace by rho A v divided by dou t. Change in density into volume divided by time. So now this term m dot accumulation I am writing in a different next slide. So m dot accumulation according to our previous equation is equal to dou rho A v by dou t. So what is constant here? Here the volume of cuboid is not at all changing. Volume of a reactor or a volume of a this bowl, that particularly wheat mixing bowl, is not at all changing, since they are the fixed region. Only the density inside that wheat flour or density inside that water is changing. So we can take out the volume component outside the derivative. So the derivative term will be just m dot accumulation is equal to volume outside. So derivative is dou rho A by dou t. So volume of cuboid is nothing but all the three direction, delta x, delta y, delta z into dou rho A by dou t. So this is entirely volume. We can consider this is a volume of that cuboid. So multiplied by change in density with respect to time. Okay, Tarun, please don't add anybody. I'm just seeing you are adding 11 number now.
No, no, sir.
Yeah, just now it came message to me. Okay, don't add everybody from now onwards. Okay,
I sent the message to add him, sir. I
who?
didn't add him.
Okay,
He
yeah,
asked
yeah.
to add, sir.
Okay, okay. Maybe just don't add anybody now, since it will create disturbance now.
Okay.
So okay,
Okay,
they
sir.
can't understand this equation in between. Okay, yeah, I'm
Okay,
just
okay.
continuing. Yeah, okay. The our next term we already defined, accumulation. Accumulation. This is the equation number 5. Okay, 5. This is the equation number 5. So next term in our mass balance is m dot generation. Okay, generation. How, when the generation will be possible in the cuboid or in some other equipment, when we are giving a wheat flour of 1 kg inside that bowl and adding some water, what is it possible? The mass balance for that wheat bowl mixing is nothing but mass of that wheat flour we supplied plus mass of that water we added. Okay, in the general sense we are speaking in the ideal condition, the mass which we for example 1 kg atta we already added in the bowl, and some 1 kg water, I am just saying in kg terms. So 1 kg water is also added. The output, the resulting output will be 2 kg. Okay, 1 kg water plus 1 kg that wheat flour. Okay, in the ideal condition, since the reaction is not happening between water and that atta, then only it is possible. Otherwise, when there is a reaction in between this water and that wheat flour, then this volume will just expand. Okay, their mass will just expand, or it will possible in either way also. Negatively it will impact, mass can be more than 2 kg or mass can be less than 2 kg, we can't say. Okay, so then the generation term, when the generation is not there, when there is generation, means there is accumulation of extra mass. Okay, when this is decelerating the mass, then we will write a negative sign, minus m dot g. So since generation is there, we are assuming, so generation term we have to take a positive term. So positively we are taking. So m dot generation is equal to, where this is only happen when there is some reaction. Okay, reaction rate. Okay, which will have a units of mole per meter cube second. Okay, rate of reaction, so mole per meter cube second, but our units needs to be kg per second. So we need to replace, what we need to replace in this equation, we need to replace this meter cube and this mole per second, so that it will obtain, it can result the equation of kg per second. How we have to do this? So this is mole per meter cube second. So we have to multiply with certain terms so that it will come into the units of our desired units of kg per second. So we have to multiply this minus Ra with a molecular weight. When we multiply with a molecular weight, what will happen? This has the units of, I am writing in separate color. Okay. Okay, this will have units of uh, gram per mole or gram per gram mole, simply we can say. So here we can directly strike out mole per mole and mole. So the units left out terms will be gram per meter cube second. So certain other terms are needed in order to get our gram per second or kg per second. So what is the term? So the only left out term will be here meter cube. So meter cube is there. We need to replace this meter cube. Meter cube is the units for volume. So we have to multiply this whole term with the volume. So volume means, just see volume. This is volume will have a units of meter cube. I'm writing in separate color, units of. Okay, so volume will have a units of meter cube. Therefore, we can cancel out meter cube and meter cube. The left out units will be gram per, here the second is there. So our required criteria already we met. So I am writing this entire equation in the next slide. So yeah, m dot g, m dot generation is equal to, which already defined, Ra reaction rate multiplied by molecular weight of that particular component A multiplied by volume. So we need to expand the volume. Reaction rate multiplied by molecular weight into volume of a cuboid is nothing but delta x, delta y, delta z. So I think this is equation, yeah, 6. Okay. This is equation 6. Okay, we already defined all the terms which are involved in our mass balance equation. Now just we have to take all this equation which are from 3 4 5 6, yeah, 3 4 5 6, this equation, from this equation 3 4, this 5 6 equation, this 6 equation, these 4 equations needs to be substituted in our equation 2. Okay, symbolically that equation is 2. So now we have to do submit equations 3 to 4 in equation 2. Okay, which is nothing, equation 2 is nothing but m dot output minus m dot input plus m dot accumulation is equal to m dot generation. This is equation 2. All the terms which we symbolically express need to be submitted in this equation. So next, in the next slide, I'm just going. So now we have to substitute every equation in that equation. Therefore, the first output equation will be ma. Okay, you don't have to confuse everything. Everything we have derived earlier. This equation, the output will be this equation. This equation we have to write there. So ma ma into na, flux of x component at x plus, since it is output we have to write x plus delta x into multiplied by the cross sectional area plus Na y component at y plus delta y multiplied by cross sectional area delta x delta z plus Na z at z plus delta z into delta x delta y. This is for output. So we have to that equation 2 is m dot output minus m dot input is plus m dot accumulation is equal to m dot generation. So this whole term, okay, this whole term is in regards to output. Okay, now we have to write it for input. So output minus input, since it is minus, so ma into nax, since these are inputs, we have to write at x delta y delta z plus nay at y delta x delta z. Due to the lack of space, I am writing in the next slide. Yeah, we have written for delta x and delta y. So we have to write the z component. Na z component, since it is output, we have to write z. So delta x and delta y we have written for the input composition. So now plus, according to equation 2, it is m dot accumulation plus m dot accumulation. We already derived. This is from equation 5, I guess. Yes, maybe 5. Yeah. Delta x delta y delta z dou rho a by dou t. So whole term is equal to generation term, m dot generation. So a generation term we have derived is rate of equation multiplied by molecular weight into volume delta x delta y delta z. We think we can express this equation number, we can give the equation number as 7. Okay, we can give this equation as equation 7. Okay, including this in the 2-slide equation. Therefore this equation is very big, so 2 slides I have used. So these 2 slides terms we have to use for equation 7. Okay, after obtaining all these terms, we have to just simplify this one. Okay, we have to just simplify the terms which we are already derived. So divide equation. Now we have to, what we have to do, divide equation 7 with volume, total volume, which is delta x delta y delta z. Then what will happen? I am doing in the earlier equation itself, so I am using different color here. Just see, we have to divide this entire term, this entire term using volume. So we have to divide with the first term will be delta x delta y delta z. When we divide this term with delta y delta x delta z, see here delta y and delta y will be cancelled out. So the left out term will be only delta x. Okay, then in the second term, okay, here also delta x delta y delta z we have to divide. So okay, the cancelled terms will be delta x which should cancel, delta z which cancel. So delta y is the left out term. For the next component, see here delta x delta y delta z we can just divide with this one. So here delta x and delta y are already there. Delta x delta y we can strike it out, only left out term will be delta z. Similarly in the input terms also same, delta x delta y delta z. So delta y delta z will be strike it out. Then next term also delta x delta y delta z. So delta x delta z is cancelled, left out term is delta y. In the next term also, see here delta x delta y delta z. So x and y is cancelled out from here, only left out term will be delta z. So here also in the next accumulation term, delta x delta y delta z. So whole term, since volume is already there, whole term will be cancelled out. In the next term also, it is delta x delta y delta z. So whole term will be cancelled out. Now we have to write the left out terms. When we divide, so we will obtain the equation as this one. So MA, okay, I am writing in the next slide. Space will not be enough. So I am writing in the next slide. So when we divide with delta x, delta y, delta z, the whole term, the left out terms will be MA at NA at x plus delta x minus NA x at x divided by left out term will be only delta x. Okay, similarly, the next component, for the next component we have to write NA at y plus delta y minus NA at y divided by delta y plus the z component NA at z plus delta z minus NAZ at z divided by delta z. Okay, these are for the three components, output and input. Now we have left with accumulation term. So mine plus accumulation. So all the term has been cancelled. Only left out term is dou rho a by dou t we are left with. Okay, dou rho a by dou t is equal to generation term, which is minus RA, rate of reaction, into only molecular weight has been left in this term. So we can give this as a equation 7, 8 we can give. Okay, we can give 8. Equation 8. Equation 8. This is equation 8. Then now what we have to do, just we have to use a Taylor series expansion. In the last class I already described what is Taylor series expansion. Okay, Taylor series expansion is used in order to evaluate a complex variable or a real variable in a simplified terms. Okay, so what is the simplified terms here? Here the simplified term is nothing but the as I already described you, inputs, all the inputs variables are already known, whereas output variables we can't define it. So we have to define all our output variables, which are complex variables, into our input variables. So what is Taylor series expansion? You can see here. So this is the important step in this entire derivation. So Taylor series expansion, we have to use Taylor series expansion, okay, which is used to evaluate the complex or real value terms. So when we define our equation as f of x, okay, when the equation is expressed in the complex terms f of x, it should be expressed in a simple terms, f of f at a plus f dash of a divided by 1 factorial into x minus a plus f double dash, which is double derivative when the function is expressed at a simple variable a divided by 2 factorial into x minus a whole square. In a simple terms, we can write for the n values up to the n derivative, f of a when derived for a nth derivative divided by n factorial into x minus a whole power n. Okay, when we performing this operation in the computer, we can express this Taylor series expansion up to the n terms. Okay, when we are doing with our hand, it is usually nominal to customary to take only two terms, first two terms, which are up to f dash of a. Okay, we can neglect the higher order terms, which double dash or f power n. Okay, up to the n terms we don't have to go. We can take first two terms and neglect the higher order terms. This is the simplification for our Taylor series expansion. So we can assume, we can relate this equation, Taylor series expansion equation. We can give some equation number to this one. So we can consider Taylor series expansion as equation 9. Yes, equation 9. Then so, okay, yeah, we have to just compare here our equation 9 Taylor series expansion with equation 8. Then we can decode this, what are f, what is x, what is a. Okay, then according to our equation, our two equation, f is nothing but na, x or at y or at z. It can take the values of NaX, Nay, or Naz. Okay. From the same equation, we can define what are our x's. X is equal to, I am writing in just simplified terms. See. So x I am expressing here. So a I am considering here. So just simply see, our primary task is we have NaX x plus delta x. This is a complex variable. We need to define in terms of A. A means simply we can say in terms of Na at x. Okay, we need to define this one. Similarly, for the yth component, Na at y plus delta y, we need to express this in simplified terms, Na at y. Similarly, for the z component, we need to express it in simply the input variables, Na at z. This is the very simplified case for Taylor series expansion. Now we can see what will happen when we substitute these variables. Now see, f can take the values of Na x or Na at y or Na at z. Okay, then x can take the values of, when it is at x, it is x plus delta x, or when it is at y, it can take y plus delta y, or when it is at z component, it can take z plus delta z. Then what are the values of a? A can take when f is at nax and x is at x plus delta x, it can take the value of x. So we have to express the whole term in terms of x. When it is xy component, we have to express in y. When it is z component, we have to express it z. This is the values which are possible. So see, now for the first component, which is the x component, we can write in Taylor series expansion. How can we write that? So according to that, our f is Na x component. So complex variable here is x plus delta x according to our previous equation. We have to write this equation in the form of a or simplified equation. So f is nax at x. So this is the first term, and second term is the derivative. So derivative is performed at first order derivative dou by dou x of already nax. For nax only we are performing at x. Okay, divided by the whole term divided by 1 factorial is there into x minus a. It is expressing x minus a. Our x is x minus x plus delta x minus x. Our a is, you can just see, this whole term is our x in Taylor series expansion. X Taylor series, Taylor. Okay, this is nothing but a in the Taylor series. So this term x and x will be cancelled out. Okay, when we cancel out this x and x terms, the left out terms, already earlier I said higher order terms will be neglected, therefore f double dash will be neglected, only the first term will be considered. So therefore the final expression will be nax at x plus delta x is equal to, we have to express in nax at x plus dou by dou x of, simply I am writing nax into left out term is delta x. Since we already cancelled out the x and this x, so left out term is only delta x. This is equation 9, I guess. This is 9, okay, already given. So we can take this as equation 10. Okay, this is equation 10. So similarly for the next component, for the next component means y component, we can write the Taylor series expansion as Taylor series expansion for the y component as Na y at y plus delta y is equal to Na y at y. When you just derive for one variable or one direction, you can write for the other two variables easily. Just we have to replace wherever x is there, we have to replace with y. Wherever y is there, we have to replace it with z. So NaY plus dou by dou y of NaY at y by 1 factorial into x minus a. So here our x is now, it will take values of y plus delta y minus y. So here we can cancel y, the left out term is only delta y. So simply we can write this equation as NaY at y plus delta y is equal to NaY at y plus dou by dou y of Na y into delta y. This is our equation 11, I guess. Yes, 11. Then see, for the same expression for the z direction we can write. How we can write? Na z at z plus delta z is equal to, we have to express in Na z at z plus dou by dou z of Na z at z by 1 factorial into x minus a. Our x now is z plus delta z minus z. So plus z minus z will be cancelled out. Left out term is only delta z. So now we can express our Na z as z plus delta z is equal to Na z at z plus dou by dou z of Na z. The left out term is only delta z. This is our equation 11. This 12. Yeah. This is equation 12. Okay. Now we already obtain our Taylor series expansion. So since we have to just substitute those terms in equation, uh, simplified equation, which is before Taylor series expansion, the equation number is 8. We have to substitute all this equation in equation 8. So substitute, next step is substitute equation 10, 11, 12 in equation number 8. Okay, all these equations needs to be substituted in equation 8. So what will happen when we substitute this in equation 8? Just we will see. The equation 8 is Ma of Na at x plus delta x we already have. So simplified Taylor series expansion need to be substituted here. Na x at x plus dou by dou x of Nax into delta x is already there. Then in equation 8 it is there, Na x at x is already there. So whole divided by the term will be there delta x. You can see from equation 8. See, in equation 8, I'm using different color. Okay, see, we are substituting in place of Nax at delta x. This term we are substituting. Yes, this term we are substituting in place of here. Okay, the next term will be there, this one. The left out terms only, these two are left out in this equation. So see, this is same as that equation. Nax at x, Taylor series expansion we already written. The left out terms are Nax at x and delta x is already there. Okay, these are the equations. Equation for the flux component in x direction. Then next component, Na y at y plus dou by dou y of Na y into delta y is already Taylor series expansion. Then already their terms are Na y at y divided by this one is already there. So here you can see this is for y component, and then for the next component I am just writing in next slide, just including plus Na z at z minus dou by dou z of Na z into delta z. Then left out terms from equation 8 is Na z at z divided by delta z. So here you can see this is the whole equation. We have to give some number here. So equation number 13. Yes. Okay, I'm just giving equation number 13 to this one. So this is equation 13. How we have to simplify this equation, we have to see now. So see, uh, NaX at x we have to cancel out, since it is already there minus NaX. So these two terms will be cancelled out. Now the left out term is this one. So delta x and delta x will be cancelled out. We can strike it out. Then NaY in the second term, and this NaY at y minus NaY it will be cancelled out, and this delta y and delta y will be cancelled out. And next term here also NaZ at z will be cancelled out, and minus NaZ will be cancelled out, and here delta z is there, in the delta z is there, will be strike it out. Okay, simply this equation 13 can be simply simplified into these terms. Okay, here the left out terms, already accumulation term we have to include here. So dou rho a by dou t is equal to some generation term Ra into Ma. Yes, these are the left out terms. This is whole equation 13. Okay, so the equation 13 will be, when we strike it out all the terms, the left out terms will be Ma into dou by dou x of Nax at x plus dou by dou y of Nay plus dou by dou z of Naz. This is the left out terms, and the accumulation term dou rho a by dou t, which is equal to the generation term Ra into Ma. This is equation 14 we can give. Okay, now this is only for component A. Component A, the same steps we have to carry it out for component B. So you need not to worry to in order to determine a component B, just this equation 14 will be written for component E directly. For component B we can write, see, here Ma is there, I am writing in different color. So here Ma is there, we need to replace this with Mb. So here Nax is there, we need to replace here with Nbx. Here Nay is there, we need to replace it with Nby. So Naz is there, it is replaced with Nbz. So rho A is there, here rho B we have to write. Here minus Ra is there, we have to write this as minus Rb. Here Ma is there, we have to write is Nb. So just simply we can write here, see, in a different color only I am writing. For component B, Mb into dou by dou x of Nbx plus dou by dou y of Nby plus dou by dou z of Nbz plus accumulation term dou rho b by dou t is equal to the generation term minus Rb into Mb. Just simply we can write this. This is equation 14, 15. Yes, this is equation 15. Okay, these are up to equation 15 or up to component B. So just simply uh, yeah, I think time has completed. Okay, we will continue in the next class. Kamal sir is taking this class. Okay, from here onwards we will complete in the next class, which is today fourth hour is there. So be on time for the fourth hour. Only the small portion of this equation has been left. So it is very important to derive a continuity equation. Many times it has been asked in your previous question papers. So I will take your attendance. Just 1 second.
సార్ రోల్ నెంబర్ 23ది కనెక్షన్ కట్ అయిపోయి లీవ్ అయిపోయాడంట సార్.
Okay.
మధ్యలో మెసేజ్ చేశాడు. మీరు యాడ్ చేయొద్దన్నారని యాడ్ చేయలేదు.
సరే అది ఇలా కనెక్షన్స్ కట్ అయిపోతే యాడ్ చేయొచ్చు, పర్లేదు. కానీ అసలు ఫస్ట్ స్టార్టింగ్లో లేట్ వచ్చిన వాళ్ళని ఎవరిని యాడ్ చేయొద్దు. అదే నా రిక్వెస్ట్. ఇంకా
ఓకే సార్.
ఎందుకంటే ఇవి అర్థం కాకుండా మనం ఆ ప్రజెంట్ వేసుకున్న లాభం లేదు దానికి.
ఓకే సార్.
నెక్స్ట్ స్టాపింగ్ ద స్క్రీన్ షేర్. ఓకే, పార్టిసిపెంట్స్. Amal sir, just
Morning, sir.
morning sir, morning. Just 5 minutes.
Okay, sir.
I took your time.
Yes.
It's a big derivation. That's why I took your time.
Yes.
Tarun,
సార్
కొంచెం అటెండెన్స్ తీసుకుంటావా? నా దాంట్లో ఇది రావట్లేదు పార్టిసిపెంట్స్ లిస్ట్. అటెండెన్స్
ఓకే
కొంచెం
సార్.
నోట్ చేసుకున్న నెంబర్స్ నేను తర్వాత కొంచెం వాట్సాప్ పెట్టవా?
ఓకే సార్.
ఓకేనా? ఓకే. Bye.
Okay.
Okay. I hope everybody understood this derivation. We will continue in the 4th hour. Okay, sir. Amal sir, thank you. Bye.
Okay,
Sir.
thank you, sir. No problem. Okay, sir.
Sir, I can't able to go out. Just drop me
Right.
out from this class. Yeah. I think my laptop has been struck.